Starting with the next topic of surface chemistry, preparation of colloids. How colloids can be prepared? Like for lyophobic colloids, we cannot directly mix dispersed phase and dispersion medium to prepare it. Some special methods are required. Like the first one is chemical method. Example, by double decomposition, that is by double displacement reaction. Arsenous oxide, when combines with H2S, we are taking the solutions of 2, and when we mix the 2, we get little big size particles of arsenous sulfide, that is, we'll get a sol of arsenous sulfide with the formation of water. Second example, by oxidation. Sulfur dioxide oxidizes H2S to form little big size particles of sulfur. Sulfur sol will form here with formation of water. Sulfur dioxide, when oxidizes H2S, it takes out the hydrogen from this, and hence we get a sol of sulfur here. By reduction, gold chloride solution, when reacted with formaldehyde and water, forms a sol of gold. Gold sol will form here with formation of methanoic acid and HCl. Gold chloride on reaction with methanol solution forms a sol of gold along with the formation of methanoic acid and HCl. A fourth example in chemical methods is of hydrolysis. If FeCl3 iron chloride solution is hydrolyzed with water, it forms a colloidal sol of iron hydroxide, ferric hydroxide, along with the formation of HCl. So these are the 4 examples by which colloids can be prepared using the chemical reactions. Second method to prepare colloids is by electrical disintegration. By electrical disintegration, which is also called Briggs arc method. Briggs arc method. Now in this process, there is dispersion as well as condensation. For Briggs arc method, electric arc is struck between electrodes of the metal. We take electrodes, current is passed through these electrodes. Here we have suspension. When current is passed through these electrodes, electric arc will struck between the electrodes. The intense heat that is produced because of this electric arc will vaporize this suspension. Normally the suspension is of metal or metal sulfide solutions. Around this container, one big size container is there in which ice is packed. Ice is packed here. So first, dispersion takes place. Dispersion means these metal or metal sulfide particles, due to this intense heat, will start separating out and will change to vapors. Since there is ice around it, so immediately these vapors, they will start condensing. And when they start condensing, this suspension will now change to colloidal soul. A colloidal soul will now form by which method? By electrical disintegration. Electricity is helping in disintegrating the big size particles now to the colloidal range. Third method, peptization. Peptization means we will take precipitates here. Precipitate particle size is big. Like for example, to understand, I am drawing the size of the particles in the precipitates like this. This is size of the particles in precipitates. Example, ferric hydroxide precipitates. To these precipitates, when some electrolyte like FeCl3 is added, then precipitates, they will change to small size particles which are of colloidal range. That is, from precipitates, now we will get the colloidal soul of ferric hydroxide. Now question here is, what is the cause of this? How this happens? How the precipitates with electrolyte change to colloidal form? During peptization, the precipitates like ferric hydroxide precipitates, they absorb one of the ions of electrolyte. This is electrolyte. One of the ions of electrolyte are adsorbed on the surface of precipitates. Like in this case, positively charged particles Fe3 plus these positive ions, they get adsorbed on the surface of ferric hydroxide precipitates. Now since positive ions are here, so there will be repulsion between the positive charged particles. Because of repulsion here, which is set up on the surface of precipitates, precipitate particles will start moving away from each other. That is, now when they will start moving away or break up into the small size particles, and around these particles, the positive particles of electrolyte, they will come. Since the size of the particles is small, so they are coming now into the colloidal range. So because of the repulsion set up here on the surface of precipitates by one of the ions of electrolyte, the precipitate particles will start separating out and they will be of small size now. That is, they will be changing to colloidal soul. And these positive particles will surround these particles now. Because of these positive particles, because of repulsion between these, now these ions again cannot combine to change back to precipitates. This is how peptization takes place. So this is the third method of preparation of colloidal souls. After this, moving on to the fourth method of preparation of colloidal souls, that is mechanical disintegration method. How mechanically suspension is disintegrated to small size particles, that is with the use of colloid mill. What is a colloid mill? There are two metal discs in colloid mill. These are the two metal discs in the colloid mill. Metal discs. And through this, from the top, a suspension is added here. In suspension, the particle size is very big as compared to the colloidal particles. So big size particles are added here, which will now come here between the two metal discs. These two metal discs, they move anti-parallel. So when they are moving, they will churn this solution, they will grind this suspension, and hence the particles will break to smaller size. So now they will come into the colloidal range. With the grinding of the suspension, the particle size will decrease and will come into colloidal range. So using colloid mill, the suspension can be changed to the colloidal form. So these are the four methods to prepare the colloids. First one is chemical method. Second is by electrical disintegration method. Third is peptization. And fourth is mechanical disintegration method. Next topic, purification of colloidal solutions or colloidal sols. So when colloidal sols are prepared, if excess of electrolytes will be there, these will act as impurities. Excess electrolyte will be like a impurity. Traces of electrolyte, some amount of electrolyte is required for the stability of the colloidal sol, but large quantities will make the colloidal sol unstable. So some amount of electrolyte is required for stability. Extra will be impurity and will make the colloidal sol unstable. So we have to reduce the concentration of electrolyte. The process of reducing, not removing, reducing the impurities of electrolyte to a minimum required level is known as purification of colloidal sol. The process of reducing the impurities of electrolytes to a minimum required level, which will make the colloidal sol stable, is called purification of colloidal sol. So by which methods colloidal sols can be purified? First method for purification of colloidal sols is called dialysis. The process of removing electrolytes or impurities from colloidal solution by use of a suitable membrane is called dialysis, and the apparatus used for this purpose is called dialyzer. So there is a bag of suitable membrane like cellophane or parchment paper. These are semi-permeable. Semi-permeable, they will let only some of the particles to pass through their pores. So a bag is taken in which impure sol is added. Impure sol is added here. These are the particles of colloidal sol, and let's say that these are the particles of electrolytes, which are the impurities. You can see the size of impurities, these particles are smaller as compared to the particles of colloidal sol. So this bag is suspended in, this bag is put in a container in which there is fresh water. There is fresh water in this. So when this bag is suspended here in the fresh water, these molecules, the impurities, particles which are of small size, they can pass through the pores of this membrane. They can come out through this membrane. But colloidal particles are of big size. They cannot pass through the holes of the membrane. So all these impurities, they will come out here, and hence this sole will be purified. And if we have to fasten this process, then here electric field is applied. Electric plates are here. The above process can be quickened if an electric field is applied around the membrane. Then this process is known as electrodialysis. Dialysis taking up the help of electricity. Quickly these ions will be pulled by these electric plates. So I am repeating the definition of dialysis now. The process of removing impurities from the colloidal sole by means of diffusion through a suitable membrane is known as dialysis. Removing the impurities from impure colloidal soles using a suitable membrane is known as dialysis. One application of dialysis is in purification of blood. In purification of blood in the artificial kidney machine. If the kidney of the person is not functioning, then the impure blood is purified by using this parchment bag or a parchment membrane in place of kidney, and this will purify the impure blood. Second method of purification of colloidal soles is ultrafiltration method. Ultrafiltration method. In this method, a specially made filter paper is used, and that filter paper is called ultra filter paper. Ultra filter paper. How this paper is made? Normal simple filter paper is taken, and it has to be soaked in Colloidal solution. Colloidal solution. What is a colloidal solution? It is 4% nitrocellulose solution in a mixture of alcohol and ether. 4% nitrocellulose in a mixture of alcohol and ether is called colloidal solution. So first filter paper has to be soaked in colloidal solution. So when the filter paper will be soaked in colloidal solution, it will be wet. Now what has to be done after this? Then it has to be hardened. Since it is wet, it has to be hardened by passing this filter paper through formaldehyde. It has to be passed through formaldehyde and then finally drying it up. So now we have to dry it. So this filter paper will be used to remove the impurities from colloidal solution. From the colloidal solution, the impurities are removed with the help of specially prepared filter paper known as ultra filter paper. So these are the methods to remove impurities from colloidal solutions. Our next topic is properties of colloidal solutions. The properties of colloidal solutions. The first property of colloidal solutions is Tyndall effect. In this case, a strong converging beam of light is passed through a colloidal solution in a beaker or in a container, any container. A colloidal solution is taken. What we have here is colloidal solution. And a strong converging light is passed through this colloidal solution, which is placed in a dark room. The path of beam gets illuminated. It gets illuminated with this part gets illuminated with a bluish light. It will get illuminated with a bluish light. This here the color will be blue, bluish light. This scattering of the light by the colloidal solution into a blue color cone is known as Tyndall effect. This cone which is formed here is called Tyndall cone. So this property is shown only by the colloidal solutions. So this can be used to distinguish between colloidal and true solutions. This property can be used to distinguish between the two types of solutions. Second property, Brownian movement. Brownian movement. When a colloidal solution is viewed under a powerful microscope, on a slide, if we take a drop of colloidal sol and view that under a powerful microscope, we'll see the particles under the microscope moving in a zigzag random way. Randomly they are moving in different directions in a zigzag way. This zigzag motion of the colloidal particles is known as Brownian movement after the name of its discoverer, Robert Brown. So this kind of zigzag movement can be seen only in the case of colloidal solutions, not in the case of true solution or suspension. So Brownian movement is a property of colloidal solutions. And because of this, one thing very important, because of this Brownian movement, colloidal sols are stable. Why they are stable? Because the particles are moving continuously. So they are not settling down. They are not settling down. And this is responsible for the stability of colloidal sols. Moving on to the next property of colloidal sols, that is the charge on colloidal particles. Charge on colloidal particles. Colloidal particles, they carry positive charge or they carry negative charge. Positively charged sols, and this side I am taking examples of negatively charged sols. Some examples of positively charged and negatively charged sols. Hydrated oxides of Fe2O3, Al2O3, hemoglobin is also a positively charged colloidal sol. Methylene blue, negatively charged sols, metals like copper, silver, gold, their sols. Arsenous sulfide sol, starch sol, Congo red dye. These are examples of negatively charged colloidal sols. Now the question here is how the charge comes on colloidal soles, origin of charge. There are different views for this. Most widely accepted view is preferential adsorption theory. Preferential adsorption theory. According to this view, according to preferential adsorption theory, the charge on colloidal particles is due to preferential adsorption of ions present in the dispersion medium. Example, like to understand this, if AgNO3 solution is added to Ki solution, AgNO3 is added to Ki solution, we get AgI and KNO3 solution. AgI here is in the form of a colloidal sole. Now, which charge is here on these colloidal soles? In this case, the charge here is the negative. Another thing is, if in place of AgNO3 adding to Ki, we take Ki and add it to AgNO3, we will again get a colloidal sole of AgI with potassium nitrate solution. But now the charge is positive. So how here it is negatively charged sole and here it is positively charged colloidal sole. AgNO3 is added to Ki. So in which we add is a dispersion medium. What we are adding is dispersed phase. Ki added to AgNO3. So here this is dispersion medium and this is dispersed phase. Sole and dispersion medium. Between the two, see which ion is common. I minus ions are common. So the ion which is common in the colloidal sole and dispersion medium, that gets adsorbed on the surface of this colloidal sole. Since here negative ions are common, so negative ions get adsorbed here and this one will be a negatively charged colloidal sole. In this case, colloidal sole and dispersion medium, Ag plus ions are common. So these common ions get adsorbed on the surface. From dispersion medium they come here on the surface. They get adsorbed here on the surface. Since positive particles they get adsorbed, this colloidal sole formed here is the positively charged colloidal sole. So preferential adsorption, it prefers to adsorb negative ions. Here it prefers to adsorb positive ions. This is one theory to explain the origin of charge on colloidal particles. Helmholtz electrokinetic electrical layer. In this topic only, one small part is there. Helmholtz electrokinetic electrical layer. Now these two examples I am taking, colloidal sole of AgI. This is a colloidal sole. Second example I am taking is of AgI colloidal sole. In first case, negative particles they get adsorbed on the surface of this. In second case, these positive particles get adsorbed on the surface of the colloidal sole. Now, since these get adsorbed on the surface, these will remain here on the surface. So this layer that is formed on the surface of colloidal sole, this layer is called a fixed layer. A fixed layer is formed on the surface of colloidal sole. So here also a fixed layer of positive ions is formed on the surface of colloidal sole. Now since negative ions are here on the surface, they will try to pull the positive ions. Since in this case I minus gets adsorbed here, K plus is left in the reaction mixture. So these negative ions will pull these positive ions also. So these negative ions will pull the positive ions, that is the K plus ions on the surface. And in second case, positive ions Ag plus here will pull the nitrate ions on their surface. They are pulling these nitrate ions here. But no bond is between the two. Since no bond is formed here, these will be close to these ions, but this layer formed is a mobile or diffused layer formed. A mobile or diffused layer is formed here. This layer formed is a mobile or diffused layer. Now, there will be a potential difference between a fixed layer and the diffused layer because these are of opposite charges. This potential difference set between the fixed layer and the diffused layer is known as electrokinetic zeta potential. Electrokinetic potential or electrokinetic zeta potential. So this is the property, that is origin of charge on colloidal soles. Moving on to the next property of colloidal soles is electrophoresis. Electrophoresis. The movement of colloidal particles towards oppositely charged electrodes in an electric field is called electrophoresis. Like if we take a colloidal sole in this U-shaped tube, colloidal sole is here in this, and we have electrodes negatively charged and here we have positively charged. Negative one is cathode, positive one is anode. So when electric current is applied to this, then the colloidal particles means dispersed phase particles, they start moving towards oppositely charged electrodes. Since the colloidal sole has some charge on it, positive or negative. Let's say here the colloidal sole that we have taken is positively charged colloidal sole. So these particles under influence of this electric field are pulled by the negative side. So they start moving here towards the negative side of this electrode. This movement of colloidal particles towards oppositely charged electrodes under the influence of electric field is known as electrophoresis. And if the colloidal particles move towards cathode, like here in this case it's cathode, then electrophoresis is also called cataphoresis. Then this is also known as cataphoresis. Next property, electro osmosis. Electro osmosis. In electrophoresis, in this, if movement of these particles we prevent some way, if we don't let these particles to go towards oppositely charged electrodes, then dispersion medium will start moving. Like here I said, the dispersed phase particles, they carry positive charge, hence they are moving towards negative side. But if we prevent the movement of these particles, then dispersion medium particles will start moving in the electric field. Then this phenomenon is known as electro osmosis. So in colloidal sole, if particles they carry positive charge, that is dispersed phase particles carry positive charge, dispersion medium will have negative charge. So if we prevent the movement of these particles this side, dispersion medium, since it will be negatively charged in this case, it will start moving this side. Then this phenomenon is termed as electro-osmosis. Next property, coagulation. The last property of colloidal soles is coagulation. If we take colloidal colloidal sol we are taking, and to this we add electrolyte. To this what we add is an electrolyte. Then these colloidal sol particles, because of addition of electrolyte, will become heavy and start coagulating. That is, precipitates they will form. Coagulation of these will take place. This is opposite to peptization. In peptization we take precipitates, we add electrolyte and we get colloidal sol. While in coagulation we take colloidal sol, we add electrolytes and we get the precipitates here. Coagulation can be carried out of colloidal sols by following methods. These methods can be used for coagulation of colloidal sol. One method is addition of electrolyte, like we have done here, by addition of an electrolyte. Second is by electrophoresis. Even by electrophoresis we can coagulate the colloidal sol. Like when electrophoresis is going on, all these particles they start collecting up here near to this electrode and they become heavy. When they become heavy, they start settling down as precipitates. That is, we can say electrophoresis is followed by coagulation. Third method is by boiling. By boiling of colloidal sols also there can be coagulation. By persistent dialysis, if dialysis will keep on doing for more time, then there will be coagulation. And one more method is there, if two oppositely charged, by mixing of two oppositely charged colloidal sols. If two oppositely charged colloidal sols are mixed, then also there will be coagulation. So these are the properties of colloidal solutions.